This time we have a speaker here, Vera, Matarese. She has tenure track position in the University of Perugia, and today she will talk to us about exoplanets.
Yes. Yes, so thank you so much for having me here today, and thank you for your kind invitation. The title of my talk is on the epistemic status of atmospheric trivial models in exoplanetary science. But before, let me give you some background information about this work of mine. So I initiated this talk when I was working with astrophysicists at the University of Bern at the Center for Space and Habitability. And it might be interesting for some of you because actually this center has a particular mission to foster dialogue between all the sciences that are actually working on exoplanet and on the other hand, the humanities, okay, in particular philosophy. And they have a particularly strong group in astrophysical, exoplanet atmosphere, okay? So this is why my work is on the atmospheric status, on the epistemic status of atmospheric models of exoplanets. So what are the goals of today? So first of all, as the title already says, I would like to investigate the epistemic status of atmospheric or trivial model, okay? So we can say that they are epistemically robust, so we can say that they are actually just a heuristic tools, okay? So that's the kind of question we're going to ask, okay? And my approach will be kind of nuanced. So traditionally, philosophers of science has this kind of dichotomy, has endorsed this kind of dichotomy between epistemically reliable methods, like scientific methods, and on the other hand, heuristic tools, okay, that allow you to do some, inferences in a very quick way and in an efficient way, okay, but they are not very reliable. Well, my approach is more nuanced because it aims to investigate the strengths and weaknesses of these models. Okay, so it will not be a yes or no answer. Yes, they are epistemically robust, or no, they are not. But to what extent are they reliable? Okay. And finally, I would like to propose that we should actually use meta-empirical confirmation tools, we will discuss about that, to discern and appreciate the epistemic significance of those models. So if you are not familiar with the meta-empirical confirmation, we will talk about that, okay? So just to tell a little bit more about exoplanetary science. So up to now, we have discovered more than 5,000 exoplanets. What are exoplanets? Exoplanets are planets that orbit around a star that is not our sun, and so they live in a solar system that are not our solar system, okay? And we know very little about them. We know very little about their formation, composition, and atmosphere. And this is because of three main challenges, difficulties, okay? First difficulty is that we have really no clue of what's going there because some of them are really novel, have novel features, extreme conditions, okay? So for instance, we have this WASP 76b, which is an exoplanet that is far away 640 light years from Earth, okay? It's 1.8 the size of Jupiter, okay? And it's an inferno-like planet, right? So it's living there, it's like living in hell, okay? So there is vaporizing iron and calcium in its atmosphere. We do not have a similar planet in our solar system, okay? So then we don't actually, we are not familiar with the conditions of these planets, okay? And so we don't have a background knowledge that we can apply to these kinds of exoplanets, okay? The second challenge is that, of course, we cannot perform in situ measurement, okay? Of course, in our dream, we can send a probe, okay? Of course, the James Webb Telescope program provides us with, very nice way to find out more about exoplanets. But, these kind of programs are extremely expensive. We cannot create one that can check the atmosphere of all 5,000 exoplanets, okay? It's extremely costly. And so we have to rely on other tools. And for now, we don't know much about these exoplanets. And the third, even more serious thing is that even we cannot even detect them in a direct way. We cannot even observe them in the direct way. Why is it so? Well, because even for the brightest and largest, biggest exoplanet that we encounter, actually, they are within the glare of this parenting star, okay? And so their lights get extinct in the glare, okay, of the parenting star. So we cannot see them, okay? So then what we would need to actually directly see and detect these exoplanets? Well, we would have to suppress the glare of the parenting star, right? And this is done with some coronagraphic tools, which are basically to put some lenses within the telescope, okay? So there are tools integrated within the telescope, okay? And because of the play of lenses, we can actually, through some interference pattern of the construction, then we can actually suppress the glare, okay, of the parenting star. But this is not enough. Okay, so we sometimes have to put an occultator in front of the telescope, okay? And all this is extremely complex, complicated, and so what we get are extremely noisy data, okay? And in any case, it's not that we can completely remove, okay, the light of the parenting star, okay? So this is a problem. We need to solve this problem. So how can we detect exoplanet? Well, we can detect them through some techniques that are indirect, okay? So that they actually allow for indirect detections and observations, okay? And this rely on the transit technique, okay? So what is the transit technique? Okay, so as you can see in the image, we can actually wait for an exoplanet to pass in front of its parenting star, okay, in such a way that it blocks the light of the parenting star, okay? So, of course, the planet must the planet has to pass exactly between us and the parenting star, okay? And then once it does, what we see is just a black kind of spot, okay? And this black spot is actually proportional to the size of the exoplanet, okay? And knowing the size of an exoplanet, you know, it's already something. And then we know that there is an exoplanet there, okay? And maybe that there are more exoplanets there and there is a real kind of solar system, okay, like ours, okay? So we see a black spot and we say, oh, there is an exoplanet, we detect it. But actually this would be extremely, you know, insufficient techniques if the only thing that we can do is just to see that there is an exoplanet, okay? So what these techniques can do is not only to allow us to indirectly detect that there is an exoplanet, but they allow us also to study the atmosphere of an exoplanet if it exists. So how is it possible? Well, this is possible because the atmosphere, if it exists, it surrounds, okay, the planet. And the light of the parenting star filters through the atmosphere of the exoplanet via transmission and absorption, okay, via scattering and via absorption. So in this way, okay, we can actually get a spectrum, okay, an exoplanet absorption or transmission spectrum. Okay, so once we have the absorption spectrum, we also have the transmission spectrum because one is the inverse of the other. Okay, so what is the spectrum? Okay, so suppose that we do not have any atmosphere of the exoplanet, then without any atmosphere, we will just get a flat line. Okay, but if there is an atmosphere, then the spectrum would show pattern of absorption and transmission of the light that comes in, okay? by the molecules or of, the gases present in the atmosphere. So basically, the gases of the atmosphere interact with the light, okay, of the planets, and at different wavelengths, right? They show different patterns. Okay, so we would have something like this. Okay. The different elements, the different chemical elements, we know they absorb and transmit the light, okay, with some specific patterns at different wavelengths, okay? So then once we have the spectrum, we can say, oh, this peak and this deep, this valley actually is a trace of this element, like H2O, okay? Or no, it's about this element, CO2. Okay, because we know that this, okay, this spectrum has a traces, a signature, okay, of the different chemical components of the atmosphere. Okay, so then what we have is a spectrum. Okay, and what we need to do is to interpret the spectrum. And in order to do this, we have the science called the spectroscopy. Okay, and the spectroscopy plays a crucial role here in exoplanetary science. Okay, why? Because the data we have about an exoplanet is more or less only the spectrum. Okay. And because from the spectrum, we can gain lots of information. We can even try to come up with hypotheses about the habitability of the planet, okay, whether the atmosphere is habitable or not, okay? So the question is, well, is spectroscopy a sound discipline, okay? Because if it is sound, so then, we can say that our knowledge about the atmosphere of exoplanet is kind of reliable, okay? If it's not, it should not be trusted, then we know that it's not reliable, okay? Well, the most important problem of spectroscopy is the problem of interpretation, the problem of interpreting the spectrum, okay? So what is this task of interpreting the spectrum? Well, as I said before, one has to identify each, traces and to reconstruct and kind of like identify to which element, okay, it corresponds, and also the abundance of the element, okay, present in the atmosphere, okay? And this faces various challenges. First of all, because our spectrum is extremely noisy, okay, there's lots of noise in the spectrum, it's not polished, okay? And also because we have to disentangle, all the information. We need to say, okay, well, until here is, CO2, until then it comes H21 and this, etc., okay? And also we know that our chemical elements in the atmosphere, they interact with the macro phenomena like haze and clouds, okay? Which of course would interfere in the spectrum, what we see in the spectrum, okay? And the most serious problem in this task of interpreting the spectrum is the problem of degeneracy, which is what we call in philosophy of science the problem of underdetermination. So the problem of degeneracy is when the same spectrum can be matched with different models of the atmosphere, so with different interpretations of the atmosphere, okay? So one team in Vera might say, oh, you see here, there is clearly H2O. And another might say, oh, no, actually it's not H2O, it's because here the atmosphere is interacting with the cloud, and so we can see here traces of CO2, like this kind of thing, okay? So then we need something that maybe cannot really break the underdetermination problem, but can at least undermine the underdetermination problem, okay? So atmospheric retrieval models have been built to try to solve this problem of interpretation in a more rigorous way, okay? Not in a definite way, but at least in a rigorous way, okay? So they are based on the challenge of inverse reasoning, and so they are built on the inverse modeling method. So what is this? Well, this is when you have some data, okay, and then you have to reconstruct, okay, why you have this data, like what is the phenomenon, okay, that leads to this particular observable data. What's, you know, and so you have to come up with different hypotheses, okay? So you have this spectrum because, and then you have to try to guess, okay, what the atmosphere would, you know, be like. And atmospheric retrieval models were constructed exactly to overcome the problem of the lack of direct measurements of observation and to solve the inverse modeling technique, okay? So here it's a diagram of what a typical retrieval model would be like, okay? So first of all, we have two different parts of the model. So we have the blue part, which is called the forward model, and we have the yellow part, which is the inverse model, okay? So the forward model, normally when we hear forward model, it's a theory-based model, okay? So from, based on some first principle, like conservation of energy, momentum, mass, etc. Okay, so based on some theory, okay, if you give an input like, well, let's think that the atmosphere is like this, these are the orange input. So we can think that the atmosphere of an exoplanet has some sort of like composition, okay? And that the gases and atmosphere has some sort of specific properties, okay? Then the forward model gives you what? Well, computes the radiative transfer. So it has inside the radiative transfer model. What is the radiative transfer model? Well, it tells you how light interacts with matter, okay? In this case, chemical components, okay? And then it gives you as output, you don't see it there, but I tell you, it gives you as output a synthetic spectrum, okay? So the synthetic spectrum is not a real spectrum, it's a spectrum that is created to tell you what the spectrum would be if the atmospheric state you chose in the beginning would be right, okay? So you choose a particular state of the atmosphere, okay? So of course you have a parameter space in the beginning with different possible composition of the atmosphere. You choose one point in your parameter space that, you know, has some specific composition, and then the forward model tells you, well, if this is your initial state, okay, that is the state of the atmosphere, okay, through the radiative transfer model, this is the kind of spectrum that you would get, okay? So of course the synthetic spectrum is extremely clean, you know, it's not noisy at all. So it's a very ideal spectrum, okay? It's a spectrum that we would never get because our measurement instruments have noise, okay? So then the task of the instrument model that you see up is to add some noise to the spectrum, okay? And to make it more realistic, okay? So first we get a very clean spectrum, then we put it in the instrument model, and the instrument model adds the kind of noise that we would get, okay? So then we have a more realistic spectrum, which however is not the real spectrum, okay? So the task of the second part of the model, okay, which is called the inverse model, basically has a particular task, which is to compare the synthetic spectrum that we get from the forward model with the real spectrum that we really got, okay, when we measure the atmosphere of the exoplanet. Okay, and then the inverse model has to assign a probability, okay, of whether, okay, this is really, you know, what kind of probability is it that this synthetic spectrum is the good one, okay, given the real spectrum that we got, okay? And then it does this until it finds the best match, okay? So once it finds the best match, then the output is, okay, we found the best match. And this is you know, that is really the synthetic spectrum with the retrieved quantities that we were really looking for, okay? Until this is not found, then the model iteratively continues to look for a new state, atmospheric state, okay? So here, one thing is important to know. So basically, if the synthetic spectrum, once compared to the data, the real spectrum, gives like no outcome. No, this is not a good match. Okay. Well, if the difference between the synthetic spectrum and the real spectrum is large, then you know, the model doesn't do anything. We have to choose another atmospheric state, okay, which is probably very distant in the parameter space from the initial one, okay, and then we give it as an input. If the difference is small, okay, the model actually chooses automatically another initial state, atmospheric state, which is in the neighborhood of the one that we were considering, okay? So this model is an iterative model, okay? As long as we get a no answer, like, oh no, you know, your synthetic spectrum does not really match the real one, then the model comes up with a new kind of guess, okay, of what the atmosphere would like, okay? So we can say that the whole exoplanetary atmospheric science inherits its epistemic status from the epistemic status of atmospheric retrieval models, okay? So the question is, well, are they reliable? Are they really sources of knowledge? So as I said before in the very beginning, traditionally philosophers of science have relied on a dichotomy between heuristics and epistemic methods on the other hand. So heuristics normally has been considered a set of strategic shortcuts, inference rules or mechanisms that enable scientists to reach some conclusion even without knowing the whole relevant information, okay? So it is adopted maybe when we have some cognitive or methodological problem, we don't have the whole information that we would need, okay? They are really efficient, but we know that they do not provide a truth-conducive solution, okay? We know that the solution might not be correct, okay? The outputs of heuristic methods are not epistemically justified, but they are pragmatically justified, okay? So heuristic methods do not provide epistemic evidence, okay? On the other hand, epistemic methods are based on some very rigorous reasoning, okay? So we know we have the whole set of information we need, okay? And then they produce an output that can be considered epistemic evidence, okay? And we know that these methods are truth conducive and that they are epistemically justified, okay? So in the beginning, my approach was exactly relying on this dichotomy. But then talking to astrophysicists, I come to realize that it's not very useful. You know, astrophysicists, first of all, they don't appreciate the difference between heuristics methods and epistemic methods. And also it's not very useful to say, well, you know, as you will see, well, these methods are heuristic, so that's it, okay? They are not really reliable. Well, so in my case now, now I have been adopting a more nuanced approach. So as you will see, for sure, atmospheric retrieval models are heuristics. So you will see that they make no guarantee that they will produce the correct solution. You will see that they are very cost effective in terms of resources, and you will see that they perform well in very idealized and simplistic scenario, but not in complex ones, okay? But the problem is that they are still good enough because heuristic methods are still good enough, okay? And my question is to what extent and why, okay? And under which aspect they are good enough, okay? So I really would like to understand and clarify the epistemic strengths and the limits of these models, okay? So the first thing I believe we should do when we try to analyze epistemic significance of models is to try to check their relation with theory and the data, okay? So a traditional approach in philosophy of science has been to divide models into two different kinds of models. Forward model, which are based on top-down approach, and they are entirely derivable from the theory. And the other hand, data-driven model, which are entirely derivable from data, okay? And they are built from a bottom-up approach, okay? So forward models normally are regarded as very strong as long as our theory is strong, right? So if our theory relies on a first order principle like conservation of mass and energy, then your model is entirely derivable from the theory, then of course it will be epistemically very robust and strong, okay? However, in cases like the scenarios of exoplanets, one weakness might be that they lack empirical grounds. We cannot really empirically test the consequences of these models, okay? Because as we saw, we cannot really, send the probe and directly measure the atmosphere, okay? Data-driven models are normally very strong because they are regarded as to have an immediate representational content. So they really carve the joints of nature. They are almost in a kind of mirroring relation with nature, okay? They're really representational. It's what is the closest to reality. However, as the work of Leonelli has shown, actually data, we never manipulate raw data. We always use the data that have been manipulated, okay? And that they have been systematized, they have been categorized, okay? And that they have been polished for noise. So normally we have very noisy data we have to polish, okay? We have to remove a noise, and that's a matter of interpretation, okay? And this is done through a work which is contextually determined. By whom? Well, by the scientific team, okay, which manages the data. And this might be done according to pragmatic interest of the team, okay? So that, having a data-based model might be weak, epistemically weak for this reason, okay? So what about retrieval models? Well, if you ask an astrophysicist, what is a retrieval model? He would say, oh, that is a data-based model, okay? But actually, that's not true. We saw the picture before. It has two different parts, the forward model and the inverse model, okay? The inverse part, okay? So retrieval models do not fit with either description, okay? They do not fit with a theory-based model. They do not fit with a data-based model, okay? They should be regarded as a hybrid, and this is constitute an interesting case for philosophers of science, okay? So in the 1990s, then there was a whole literature talking about another kinds of models. So Morgan and Morrison in 1999 and Cartwright also in 1999, and they were talking about models that are independent from both the theory and data, okay? They were saying, no, we can't say that models are entirely derivable from one or another. Actually, they have their own status. The status as mediators, between theory and data, okay? And they are independent, okay? And then one powerful image to understand the model is, like a cook who, cooks something without a recipe, okay? Well, that's how scientists cook up models, okay? Well, now, I do not think that retrieval models actually fit with the description either, okay? Because it's true that they are not entirely derivable from theory, and they are not entirely derivable from data, but actually, even though they are not reducible to one or another, they are derivable from both, okay? So they do not really enjoy much dependence, okay? So they are dependent on both the theory and both the data. Why is it that? Well, of course, there is the radiative transfer model, okay, inside the forward model, but that's, you know, entirely derivable from first order principle of energy mass conservation. And then, yes, the second part is is dependent on the data, okay, the data that we actually gain, okay, and that's it, okay. So it's true that in the forward part we have the instrument model, but that's also a model based on the kind of data that we have, you know, the kind of instruments that we have and the kind of noise that it adds to our data, okay? So what about the epistemic value of retrieval models that are derivable from both theory and both data? Well, one might think, look, you know, they inherit all the weaknesses from both theory-based model and the data-based model, okay? Why? Because they have both. So retrieval models contain a theory-based part and the data-based part. So basically they inherit the limits of a data-based model and a theory-based model. But actually my claim in my paper is that actually since they are jointly constrained by both the theoretical elements and data elements, the strength of one part, the forward part, compensates the weakness of the data-based part and vice versa. So let's think in this way. So theoretical models are sometimes criticized because, oh, they lack empirical ground. Well, but we have the inverse part, right, where there is a data that is compared to the synthetic spectrum, okay? So we know that, you know, we have some empirical constraint. And then on the other hand, we have the problem of database models. Oh, but you know, but maybe our data are so noisy. Maybe we have not been able to identify the noise. Maybe they have been manipulated too much. Yeah, okay, but you know, this kind of the output that retrieval models give is constrained by the theory, okay, by theoretical principle, and a very strong, like, conservation principle of energy momentum. So this makes retrieval models more reliable than pure data-based model or theory-based model. That's my claim. Okay. The second thing that we have to look into when we want to evaluate the function, the epistemic significance of atmospheric retrieval models is the epistemic function. Okay. In this case, it really seems the astrophysicists build atmospheric retrieval models with a realist quest to know what's going on out there, okay, in the outer universe, okay? Do you really want our models, atmospheric models, to really tell us whether there is water or CO2 or other elements, okay? So this is a representational function that is in terms of a mapping to state of affairs, okay? So there is some facts going on there, some affairs, and then we want to model that truly in a kind of like mirroring relation, okay, represents what's going in there, okay? And then our model, okay, can explain things. For instance, it can explain the kind of rotation that exoplanets have. In a very kind of realistic way, it's this kind of explanation, like in a kind of causal way, okay? So the thought is we want to produce, to develop models that give us epistemic evidence of what's going there, you know, on the exoplanets, okay? There's a problem. And the problem is that atmospheric retrieval models suffer the problem of incompatible models, okay? So the problem of incompatible models, or also called the problem of style is a problem that has been identified by Guyen and also by Morrison, and then also by Michela Massimi recently has been discussed, okay, which is when you have a different representational models, all targeting the same target, okay, all wanting to represent the same target, but then they give different outputs, okay, they give different representations, okay. And it seems that atmospheric retrieval models suffer from this problem, are vulnerable to this problem. So until 2020, actually, no astrophysicists were doing any kind of intermodal comparison. Why? Well, because the progress was really meant like, we want to find out more and more atmosphere of more and more exoplanets, okay? Why should we waste the time in our teams to perform again retrieval models for exoplanets that have been already, you know, discovered and studied? We know all about the atmosphere. But then in 2020, Barstow and her collaborators started to say, well, no, let's try to check whether different models, retrieval models, give the same output. And she tried with 3 different suits or different codes, different models, Tarex, Nemesis, and Chimera, and they all function exactly as I was telling you before, how typical retrieval models work. So how did this comparison how was it constructed? So first of all, they wanted just to compare the forward part, okay, with extremely simplistic or idealized kind of atmosphere. So they were, you know what, let's just think that our exoplanet atmosphere is just one gas, okay? And that's it. We don't want to make it more complicated, okay? And let's just try to check whether they give the same synthetic spectrum and retrieve the quantities, which are the quantities associated to the spectrum, okay? And then, well, it was already quite difficult to get the same synthetic spectrum, okay, with associated quantities. Why? Well, because at the very beginning, we have to actually not only imagine a composition of the atmosphere, but also like properties of the gas of the atmosphere. So for instance, will gravity acceleration, gravitational acceleration affect our gas, which, you know, has, you know, is spread, okay, in the atmosphere at different altitude, okay? And maybe, you know, one team will say, well, no, let's think that, you know, there is no effect, okay? And the other was like, oh, no, we model, you know, we put some effects, okay? So the gravity, the gravitational acceleration will have an impact, okay, depending on the altitude, okay, where this spectrum is spreading. Okay. But one that is fixed, and so there is kind of agreement, then we get the same result, okay? The second part was to compare more realistic forward models, okay? And that was already even more challenging. So there was agreement generally, but the outputs were differing at the level of several tens of particles per million, okay, which is a unit talking about the concentration, okay, of the molecules of the gas, okay? So basically already, you know, at a finer grain level, then we can see some differences. So the models give some differences, okay? And the third step was really to compare the inverse modeling part and to say, okay, you know what? We take the output, okay, of Taurex, for instance, which is one suit, one model, okay? And then we use it as an input, okay, for the other 2 models, and we ask them what's the best match, okay? And we see whether there is agreement or not, okay? Whether the synthetic spectrum and the retrieved quantities of, in this case, Nemesis and Chimera, okay, are the same as the synthetic and retrieved quantities of a Taurex, okay? And again, like there were differences, okay, at the level of several tenths of ppm, okay? So then, yeah, there is, to one extent, there is agreement, but then when we look at things, at, more in details, then we see that there are differences, okay? So then, there is a kind of literature in philosophy that can help us with this problem. And this is the literature on perspectival models developed by Michela Massimi. So perspectival models are a kind of models that have been developed exactly to overcome this problem of incompatible models. So they say, well, look, it's true, like, make sure science is giving us different representational models, so all targeting the same target, okay? But we should not look, we should not understand their functions in terms of mapping to state of affairs, but in terms of conveying modern knowledge. So these different models give us some model knowledge because they tell us what's possible, okay? What's physically possible, okay? So, how this how is this happening? Well, first of all, we have some forward model. Okay, the forward model, they map the space of what's possible. Okay, with the parameter space and so on and so forth, and then they make all these hypotheses testable. Okay, because they produce the syntactic spectrum. Okay, and then. Okay, they compare the syntactic spectrum with the real spectrum, and by doing so, they rule out different possibilities, and so different possible atmospheric models. Okay, so basically these retrieval models, okay, they are representational and they advance scientific progress, not in terms of a mapping to state of affairs, but because they tell us what's not possible, what's possible, what's even more probable, okay? So in this sense, they provide epistemic guidance, okay? Then, of course, when I think about this guidance, I think that it has very important limits. So why it has to, well, the fact that atmospheric retrieval models suffer the problem of incompatible models means that maybe if we use like Taurex or Nemesis, okay, or Chimera, well, each of them might have this problem that it might be not looking into the right space of possibility, right? So maybe when, we start with our initial kind of state, we might be not looking into the right parameter space, okay? Maybe we are not putting all, the parameters that we need to, okay? So this has been called, in the context of eliminative reasoning by Casey McCoy, the problem of justification of space of possibilities. How do we know that we are taking into consideration the whole set of hypotheses in the first place? How are we constraining this space? Okay. The second problem is that, well, each model might be actually looking at the right space of possibility, but the models that have just a limited number of guesses, okay, of iterations. So it might be that the model does not stop at the best match, okay? So it might be that the model is not able to identify the best match because we start looking at a region of space which does not contain the best match, but that's good enough, okay? So, sometimes in this iteration, so the model starts with, a region of space, and well, they say it checks and evaluates that it's not good enough, and then it goes to another parameter, space point, and then it says, well, it's okay, and then it goes a little bit, farther away, and says it's totally wrong. Okay, so, okay, no, then, that was, it goes back and says, no, that was the best match possible. But maybe, the best match is in a very distant region of parameter space. Okay, and since the models just have a number of finite guesses or iterations, then it might not be looking into the it might not be ever find, right, the best match. Okay, the model does not check, does not span the whole space of possibility. Okay, so what can we say up to now about the epistemic import of retrieval models? Okay, so first of all, they tell us what's, you know, objectively possible. Okay, and decides what is objectively most possible in a kind of rigorous way within the model. They make some theoretical hypothesis, okay, and they check it, with real data, okay. They tell us what's the space we should not be look, and what's the space in which we should be look, if we want to find a true solution, okay. And we can also say that this is not just a mere exploratory heuristic rules, but it's really connected to the goal of giving us a model knowledge about the target system, okay? So they provide a genuine guide for the possible combination of the atmosphere parameters, okay? And that's how, they contribute scientific progress by ruling out rival possibilities, okay? But attention, because, sometimes, okay, we know that we should not just take for granted one model with one input, but a family of models, okay, which are all the best solutions of a different model, okay, different outputs that are the best outputs of different retrieval models, okay, because of this problem compatible models. So the conclusions right here up to now is that, well, they do have some kind of justification that is better than a theory-based model or data-based model. Okay, they are more reliable. Okay, they do have a representational function as they convey model knowledge, but then they cannot really be considered pieces of epistemic evidence because of the problem of retrieval models. So then here is my proposal. Well, this seems a little bit too weak, okay? It's just all in terms of what is performing, what model is performing better than another one, okay? And it does not give us real epistemic evidence for now, what we have been saying. So my proposal is, isn't it that this is a case where meta-empirical confirmation tools work very well? So let's try to see why. So meta-empirical confirmation is really, I think, able to help us appreciate and discern the epistemic import of these models. So this is a framework that has been developed by Richard David and has been also developed by McCoy and Siska de Bedermaker and David. I also employed it in a paper on Oumuamua. And it is stronger than just Bayesian confirmation, okay? And it's usually endorsed and applied where empirical confirmation is not possible, okay? So how does it work, okay? So we have our hypothesis here, which is H, and H is a possible hypothetical model of our atmosphere, like model in the sense that it's a possible representation composition of our atmosphere, okay? And we do not have any empirical evidence that directly supports age, okay? So what we do is to find some meta-empirical evidence F, okay, that, is the base for some meta-empirical arguments, okay, that all conforms Y, so increases the hypothesis of Y, which is the hypothesis of limitation to local underdetermination, which we will see what it is, and then Y then increases the probability of age, okay? So what is Y? So Y is the hypothesis that, so I apply it to our case, so the case of atmospheric composition. So it's the hypothesis that there are no, or there are only a few alternative atmospheric combinations that can be empirically distinguished in a specific empirical horizon given by the real spectrum that is being used, okay? So basically going back, so we need some empirical evidence that confirms that there are no or few alternatives, okay, for our atmospheric compositions. And the fact there are not many alternatives increases the probability that our age, and so that our atmospheric composition, the one that is a given, that is a hypothetical, is is a probable, is the true one, okay? So what are the meta-empirical arguments? So Richard has developed 3 meta-empirical arguments, but there may be more. The list is not, exhaustive, okay? And then in the following, well, I will use A for the atmospheric composition that is the outcome, of an atmospheric retrieval model, R, okay? And so that is the best fit. So A is the best fit for a given spectrum S of an exoplanet AE. Anyway, now we will. So the meta-empirical arguments are 3, okay? So the first one is a MIA, which is a meta-inductive argument. So in the past, atmospheric compositions that satisfy the same given set of conditions that A, and so the best output, okay, of our model, satisfied, have shown a tendency of being viable, okay, for exoplanets similar to the one that we are studying. Okay, so we have a retrieval model. It gives us as output a particular atmospheric composition A. Okay, is it really, the right one? Well, we see that in the past, okay, the same atmospheric composition, okay, was similar atmospheric composition was given as output for exoplanets that were similar to the exoplanets that we're studying now, okay? So the fact that this happens, okay, can be explained by the hypothesis Y, the hypothesis of the limitation to local underdetermination, that there are just few alternatives to our A, okay? So for this reason, the observation that, that in the past there were a similar atmospheric composition, were found for similar exoplanets, is taken to increase the probability that A is viable also for E. Then there is another argument that says, well, look, suppose that a team finds out with a retrieval model this atmospheric composition A, that is the output of the retrieval model, okay? And after a while, they find out that this A can also explain other problems, okay? For instance, the rotation of the exoplanet, okay? So then the fact that this atmospheric composition A actually can explain a different phenomena, okay, or reveals unexpected exploratory interconnections, okay, can be explained by the hypothesis Y, okay, that there are few alternative hypotheses, okay, that in the given concept that there are conceptual aspects of the phenomenology that await explanation. So there are less number of alternatives than the number of phenomena that need to be explained, okay? And this is an indication of the viability of our hypothesis H. And then there is a very simple non-alternative argument. Well, scientists have looked intensively for a considerable time for alternative atmospheric composition different from A that could match the spectrum S, but they haven't found any. Okay, and this can be explained by the hypothesis Y that there are few or no possible alternatives to our hypothesis H. And this is taken as indication of the viability of our hypothesis H. Okay. So of course, here with in AA, we have to be careful, okay? Because first of all, it can be applied within one particular model in the sense that we have explored lots of the space, okay, or the parameter space, okay, but we haven't found a better match. But also, it should be applied for other models because we know that atmospheric trivial models might be vulnerable to the problem of incompatible models, okay? So if, you know, other models give different outcomes, then we know that we have to take into consideration a family of outputs, okay? So then in this case, atmospheric trivial models still function just as perspectival models, and so just telling us what's possible, okay? Each offers just a partial perspective of what might be looking, you know, like the atmosphere, okay? However, it should also be noted that the non-alternative argument is not alone. So if, for instance, the non-alternative argument supports a first, but not a second, not a third. So it supports just one output of one model, but it doesn't, So in case the non-alternative argument supports internally one model, the output of one model, and also the output of the second model, the output of the third model, the output of the fourth model, okay? But Mia and Vera, which are the two other arguments, just support the output of one model, but not the other, okay, then we can say, well, look, the meta-empirical arguments converge to just one output and not the other, not the others, okay? So our confidence in one output of one model is justified, okay, by the fact that all like NAA and EMEA and Vera all support that one, okay? Okay, so one objection is, well, look, but I mean, the thing is that the epistemic import of these models is not intrinsic in this model, okay? It's just extrinsic, okay? It's extrinsic in the sense that we are just applying meta-empirical tools to the model, okay? Well, for NAA, for non-alternative arguments, not exactly true because it's built within the models how many times it has to look for the right solutions. And we can also decide whether it should look for really large region of parameter space or not, okay? But also, since in the models we have to assign priors to the different possible atmospheric composition, okay, then we can also take into consideration meta-empirical arguments before assigning the priors, okay? So we can say, well, given that the meta-induction argument supports this particular hypothetical composition, then my priors are a bit, a bit higher than, the priors for other possibility, okay? So these models tell us that the meta-empirical confirmation tools tell us whether these models, the outputs of these models are viable or not. Okay, what does it mean viable? Okay, well, viability is a bit weaker than truth because it's bound to a specific research context. Okay, so we are saying that there are no alternatives to a particular model given a specific empirical horizon. Okay, however, it remains an epistemic virtue. It's not merely pragmatic. Okay, and so it's an epistemic goal in its own right. Okay, so here it's my conclusion. Okay, so exoplanetary science is a young discipline. Okay, there is a genuine opportunity for philosopher science to jump in and contribute to discussions about validity and the robustness of its model. Okay, and the growing attention that it's receiving from astrophysics is telling us that it's it's a time for us to get involved. Okay. I think it's very important not to overlook or downplay the challenges of exoplanetary science, okay? And what are my achievements of today? Well, I think that atmospheric retrieval models are more robust than just the theory-based or data-based models, and are also more robust than independent models. They have a representation of function in terms of model knowledge and not in terms of mapping to state of affairs. They may or may not provide an epistemic justification that is stronger than Bayesian confirmation if they use the tools of meta-empirical confirmation. So basically, if we use the tools of meta-empirical confirmation and in order to check the viability of these models, it may or may not turn out that these models produce epistemic evidence, okay? And yeah, with this, I would like to thank you for your attention, and I look forward to your question. Thank you.